An application of similar triangles that we actually already looked at when we were solving proportions is this idea that you can use shadows to help you determine similar triangles to solve for lengths. So in this case, we have a silo that casts a 24-foot long shadow, and we have a 4-foot pole that has a 3-foot shadow. And since the sun is at the same point right now, that angle is going to be the same, and we have the perpendicular angle that's the same, which means the third angle would have to be the same since all triangles have 180 degrees when you add their angles. So we know that these are going to be similar triangles. So let's set this proportion up. 24.0 would correspond with 3.0. Then H needs to be in the top because that corresponds to the same triangle that 24 came from. And then 4 is the corresponding side on the smaller triangle. So we need to cross multiply. 24 times 4 is 96 equals 3H. We divide by 3, and H needs to be 32. So that tells us the height of this silo is 32 feet. So similar triangles can be very useful when you're trying to find an unknown height. Now take a look at example 8. We're drawing a map where we're going to have a scale, and the scale will be given to you on the map. In this case, 1 centimeter is representing 200 kilometers in the real world. So we're going to measure the distance between Chicago and Toronto on the map. If we measured that to be 3.5 centimeters, if we wanted to find the actual distance between Chicago and Toronto, we would use this scale factor and this idea that these are similar triangles. So we're using the similarity idea. We're not necessarily making a triangle here, but we are using this idea of similarity when dealing with scale drawings. So you would want to be consistent. And so I'm just going to remind myself I want to use the map to the real. So here, 1 centimeter equals 200 kilometers. And I'm going to leave off the units. It just makes things a little bit easier when I'm trying to solve. So 1 to 200. And then on the map, and this is why I have to write this out, the map goes up in the top. That's 3.5. I need the actual distance. So let's cross multiply. We get x equals, it's just 1x, so I can leave off the 1. 200 times 3.5 gives me 700, and that's all I need. The distance between these two cities is actually 700 kilometers. And then another application here, still using this idea of similarity with scale factors. We have a satellite photograph that reveals 3 missile silos an equal distance apart. The images of the silos on the photograph are 2.0 millimeters. Now, based on other photographs and other satellite data, we know that 1 millimeter on the map equals 0.429 kilometers in real life. So if we want to know the actual distance between the silos, we're going to use the map to the actual. The map says that they are 2.80 apart. We don't know the actual. And then the scale of the map is 1.00 over 0.429. And here I did it a little bit differently. I didn't take the known values and write those first. It doesn't matter the order that you do these. So if you do, the X on the left, it's okay. But we cross multiply. 2.8 times 0.429, I get 1.2012 equals 1x, and that's all I have to do. This tells me that based on the units, the actual distance is in kilometers, and so these silos are 1.2012 kilometers apart.